Today I will discuss about the another method of forecasting. The method is auto-regressive moving average method. The short form of this auto-regressive moving average is ARMA. Auto-regressive moving average model combined of auto-regressive the shortest form of autoregressive is AR and moving average, that is MA. Components to forecast stationary time series data. Already we discussed about moving average method in time series data. We find trend using moving average method in time series data. Autoregressive moving average means autoregressive model and moving average model combination. The model notationally written as ARMA bracket in bracket P comma Q models, where P is lagged observation, where P is lag observations or order of AR autoregressive model, and Q lagged of lagged forecast error or order of MA model moving average model. To predict future values. These models are effective from short-term forecasting and analyzing data structure with linear dependencies. This is the description of autoregressive model. The question is describe the autoregressive model, then we write this. Now we discuss component of autoregressive model. ARMA model. First is autoregressive. AR part. Predict the current value based on a weighted sum of previous value. This is known as autoregressive. Predict the current value based on a weighted sum of previous values. This is known as autoregressive. Number 2, moving average. Already we discussed this moving average part in trend finding but trend calculation part. Uses the dependency between an observation and residual errors from previous prediction. This method applicable for finding trend. Number 3, order P, Q. P means lag observations. And Q is the lagged forecast error. What do you mean by lag? We discuss about lag in using by time series data. Lag is the difference between past values time period. For example, time series data, time and values are given. Like monthly data, January, February, March, April. The data is values is present x1, x2, x3, x4. Lag for April. We find the lag for April. Lag 1 March equals to x2. Lag 1 means previous month with one gap. So previous month of April is March. So lag 1 is March. Lag 2 is the difference of two time period. This is lag 1 April to March to April, and secondly March to February. So lag is 2. Here lag for April is February equal to x2. Lag 3 is January x1. Why January? April to previous 3 time period is January. So lag 3 is January. So this is the lag. Now we discuss about stationary data. stationary data. A time series data is said to be stationary if the mean variance and autocorrelation do not change over time. A time series data is said to be stationary if the mean variance and autocorrelation do not change over time. টাইমের রেসপেক্টে with respect to time, the mean of the data, variance of the data and autocorrelation of the data not changed, then the data is called stationary data. Now we discuss about ARMA model order PQ. The model is xt equal to lambda plus summation I running from 1 to p phi I xt minus I plus j running from 1 to q theta j et minus j plus et. This is the model of ARMA order PQ. The general form of this model is that equal to lambda plus the value, the expansion of this summation is phi 1 xt minus 1 phi 2 xt minus 2 dot phi p xt minus p plus expansion of this summation theta 1 e t minus 1 theta 2 e t minus 2 dot theta q e t minus q plus et. This is the expression of the above equation if we expand the summation formula. So this is the structure of ARMA model, where xt is the time series parameter. This is denote the time series parameter. Phi 1, phi 2, phi p are parameter coefficient. For AR model, theta 1, theta 2, theta pi, theta q parameter coefficient. For MA model, moving average model, ET is the noise or error. We already discussed about noise in model parameter estimation forecasting data. In forecasting data, there are two parts. One is signal, another is error. This error is known as noise, and lambda is the constant. So the model of ARMA order PQ is denoted by this, and their expression is also same by applying summation, and the meaning of all term are given. Now we discuss about another model. The model is ARIMA, autoregressive integrated moving average. Autoregressive integrated moving average model. A autoregressive integrated moving average models are statistical technique statistical techniques used for analyzing and forecasting time series data by looking past values, trends, and error. The model is combination of AR lagged values, I, that is differencing to make the data stationary. That's mean integrated, and MA lagged errors components. It denoted by parameter PDQ. It is widely used. It is widely used for forecasting future data, future trends based on historical data. So, autoregressive integrated moving average model. A autoregressive integrated moving average models are statistical technique used for analyzing and forecasting time series data by looking past values, trends, and error. We find the integrating model using past values, trends, and error. The model is combination of three types of thing, like AR, autoregressive, I for integrated, and moving average MA. It denoted by parameter PDQ, P for air, I for D, and Q for moving average. It is widely used for forecasting future trends based on historical data. The model used for future trend, forecasting future trend based on historical data, previous year data. So this is the ARIMA model, auto-regressive integrating moving average model. There are three parts: auto-regressive part, integrated part, and moving average part. Auto-regressive part have parameter P, integrated part has parameter D, and moving average part is parameter Q. All are lag. Now we discuss about stationary data. Stationary already defined. Stationary is the time series data. Stationary time series data is the data where constant mean, constant variance, constant autocorrelation. Here mean, variance and autocorrelation are constant. Some type of stationary data we discuss. Type 1, strict stationary. Strict stationary. Strict stationary, a time series data as time series is said to be strict stationary if the joint distribution of any set of time indices is the same for all time points. A time series is said to be strict stationary if the joint distribution of any set of time indices is the same for all time points. For every time points, the joint distribution have same values of indices like mean, autocorrelation, variance. Number 2, weak stationary. That is also known as second order stationary. The time series is weakly stationary if it satisfies the three conditions. Three conditions are constant mean, constant variance, and constant autocorrelation. That is expectation of xt equal to mu. Expect variance of xt equal to sigma square, and covariance of xt comma xt minus h equal to lambda h, where h is the lag and for all t, for all t expectation of t equal to mu, for all t expectation of variance of xt equal to sigma square, and covariance of autocovariance. This is the not correlation, this is autocovariance, constant autocovariance. Also, covariance between xt and xt minus h is constant for all t, and h is the lag. Lag is the difference between two time period, we already discussed. Here t is one time period, t minus h another time period. T minus lag is the difference, t minus h equal to h. H is the lag. Next we discuss stationary series. A series of data is said to be stationary series if random noise, fluctuations around time period is a constant mean, is a constant. Next, non-stationary. A series of data is said to be non-stationary series if in data trend is present. Already we discussed about signal and noise. Signal is the trend part or seasonal variation part of the time series data is known as signal, and another thing is noise. Noise is the fluctuation part or random part of the time series data. Here same, stationary series means in the data fluctuation present, and non-stationary mean trend present. If trend present, then the mean variance and covariance are not constants. So non-stationary data we get if the data have trend, but we get stationary series of data when the data have no trend. Now we discuss autocorrelation function. The full form of this is the full form of autocorrelation function, and the short form is ACF. The autocorrelation function ACF measure the linear relationship between a time series xt and its lagged, that is past values, xt minus h, where h is the lag. The autocorrelation function is denoted by fh. fh equal to covariance of xt comma xt minus h by root over variance of xt root over variance of xt minus h. Range of fh always belong to -1 to 1. -1 less than equal to fh less than equal to 1. The range is -1 to 1. fh close to 1. If fh close to 1, that means strong positive relation. Strong positive relation between two data. If fh close to -1, that means strong negative relation. Strong negative relation. If fh close to 0, no relationship. No relationship exists. For stationary data, autocorrelation declines quickly and for non-stationary data, autocorrelation declines slowly. Autocorrelation is the important part of the forecasting. If autocorrelation is constant, then stationary data present in time series. Autocorrelation is not constant, then non-stationary data present in time series. Now we discuss about some test for stationary data. Test for stationary data. First test is আগমেন্টেড ডিকে ফুলার টেস্ট, এর শর্ট ফর্ম হচ্ছে এডিএফ টেস্ট। আগমেন্টেড ডিকে ফুলার টেস্ট, short form is ADF test. ADF test is a statistical test in time series analysis. Used to determine whether a given time series is stationary or not. We know a stationary time series has constant mean and variance over time. The test is the hypothesis test. So there are two hypotheses exist. One is null hypothesis, that is denoted by H naught. Another is alternative hypothesis, that is denoted by H1. Null hypothesis of this test is the series is non-stationary, and the alternative hypothesis of the test is the series is stationary. In hypothesis state, we always test for null hypothesis is rejected. We always expect the null hypothesis is rejected. So here we reject the null hypothesis. That means the time series is non-stationary, is false. So we get the series is stationary. How to test? We test the rejection rule using the p-values. In hypothesis test, p-value is the important part. Already you know about p-value. The rejection rule if p-values less than 0.05, we reject H naught, and it implies the series is stationary. If p-values greater than or equal to 0.05, we reject H1. H1 means the data is series is stationary, we reject, and it implies the series is non-stationary. In this way we test ADF, augmented Dickey Fuller test for stationary. Next test is KPSS test. The KPSS is the combination of 4 statisticians. Their name we write. In KPSS test is same as ADF test. The KPSS test is used for accessing the stationary of a time series. Here also we test using hypothesis. So two hypotheses are needed. H0, H1. H0 here, H0 is the series is stationary. And the alternative is the series is non-stationary. Okay. If p value less than 0.05, reject the null hypothesis. If p value greater than equal to 0.05, fail to reject null hypothesis. So this is the same but opposite of ADF test. And last one is using differencing. Using differencing, we prove the data is stationary or not. If the difference series become stable, it implies original series was non-stationary, and if the differencing series is still unstable, differencing unstable if the series is stable, it implies original series was non-stationary, and if the differencing series is still stable, it implies original series was stationary. This differencing have a equation. The model of differencing xt dash equals to xt minus 1. Find differences of consecutive observation. Xt is the observation at time t, xt minus 1 is the observation at time t minus 1. xt হচ্ছে observation at time t, xt minus 1 is the observation at time t minus 1. xt dash is the differencing between observation at time t and at time t minus 1. Last, another test is unit root test. The unit root test helps determine whether a time series is stationary or not. কিভাবে প্রুভ করে a time series has a unit root it is non-stationary. Otherwise stationary. The model of unit root test is xt equals to rho xt minus 1 plus epsilon t. Rho is the parameter, epsilon t is the noise or error term. If and xt the time series observation value at time period t, xt minus 1 is the time series values at time t minus 1. If rho equal to 1, that imply non-stationary. If rho modulus of rho less than 1, that imply stationary. This fourth type of test we apply to prove the time series data is stationary or not. 4 type of tests are most important for this chapter, applicable for theoretical question.